Now we're going to start looking at compound events and revisit or probability, which can be for compound or actually other events, single events. So we'll start with an urn, which has four marbles in it, two red, one green, one white. And I'm going to make a sample tree here. And you don't really have to make the sample tree. It's very helpful to have the outcomes. I'm not too worried about dupes or which order. I'm just saying, here's red marble one, then you get red marble one. But this will help us illustrate the probabilities and how this works. All right, so with dupes, how many outcomes are there? So if I count red, red, and red, red is two different, then I have 16 outcomes. Now, how many outcomes had a green marble first and then a red marble second? These two did. And so I have two outcomes with the green marble first and the red marble second out of 16. So if I were to ask you the probability of drawing a green marble on the first draw, what would you think it would be? Well, on the first draw, there are four marbles. One is green. So you should hope that it is 1 out of 4. And you can kind of see this in our tree diagram here. Now remember, I'm putting the marble back. So if I put the marble back, what's the probability I draw a red marble given that I drew a green marble? Well, there are two outcomes here that out of 4, so that probability is 2 out of 4 or 1/2. Now, what's the probability I draw a green marble then a red marble? Well, there are two outcomes here for green then red out of 16. So it's 2 out of 16 or 1 over 8. But there's actually a shortcut when you have compound events. You can multiply the probability of the first times the probability of the second. So I get 1/4 times 1/2 equals 1/8. I don't know if you notice this little line here. This is probability of getting a red given that I had a green. Well, it didn't really matter if I had a green or a red or a white. The probability of getting a red on the second marble was 1/2. And so we're going to go ahead and see, well, why do I bother to write it that way? Well, we're going to redo the urn again. And this time, instead of putting the marble back, we're going to keep it and draw a second marble. So I'm going to go ahead, if I keep the red marble, then that branch disappears, and this branch disappears. The green disappears here, and the white disappears there because those marbles are no longer available if they are drawn on the first draw. So how many outcomes had a green marble first and then a red marble second? Same two outcomes, right? Green and red and red. What is the probability we draw a green marble, then a red marble? Well, there are two outcomes, and this time I've gotten rid of some outcomes here because I can't have white and white. There are only 12 total outcomes, so the probability of green then red is 2 out of 12, or 1/6, assuming these are all equally likely, and in this case they are. Now, what's the probability of drawing a green marble on the first draw? That hasn't really changed. It's still 1/4. But what has changed is if I tell you I drew a green marble, what's the probability of getting a red? It's actually 2 out of 3, all right? And if I multiply them, I get 1/4 times 2/3. You go 2 over 12, which simplifies to 1 over 6. So the multiplying rule works well here. The main thing you have to keep in mind is the given. So if I was doing red then red, I would say, okay, the probability of getting a red on the first marble is 1/2, right? And then the probability of getting a red again is 1/3. And that would give me 1/2 times 1/3 is 1/6. All right, now let's talk about independent versus dependent events. Both the marble problems I showed you were examples of independent and dependent events. If A and B are independent, then the probability of event B occurring is not affected by event A. And the way we say it is, oh, the probability of A given B is just the probability of A, because it doesn't matter if B happens or not. Or probability of B given A is just the probability of B, because it doesn't matter if A happens or not. Now, this is true when they're independent, but if events that occur without replacement, when we keep something out, we're changing the probabilities, those are typically dependent. So you were expected to know how to tell the difference between independent and dependent events. Well, in the choice A here, drawing a marble from an urn, replacing it, and drawing a second marble, that's like our first example that we did. And that was independent. Rolling a die and drawing a card. The card doesn't care what you rolled, so that's also independent. Drawing two marbles from an urn. So it sort of implies here that you're keeping the marbles. So we would say that's dependent because once you keep one, there are less marbles in there and it affects your probability. Rolling a die twice is independent because a die doesn't, it's not like suddenly you roll a 2 and 2 disappears off the die. It's still there. Rolling a die and flipping a coin, independent. Drawing a card and flipping a coin, also independent. Flipping a coin twice, it's not like heads is going to disappear because you flipped heads. So that's independent. But drawing two cards from a deck, if you draw an ace and you're like, oh, what's the probability I draw another ace? Well, you already have one. That's our, and not only that, you've affected the total amount of cards. Instead of 52 cards, now there's 51. Instead of 4 aces, now there are 3. So that is dependent. This leads us to the multiplication rule of probability. So if you want to know the probability of doing one thing and then another, and that's where the and symbol comes here, it's probability of A and multiplied by probability of B. You can also write it this way to indicate given, because sometimes that probability of B depends on what happens with A. So let's cover this example. I pulled these numbers from the Round Rock Express early in the season, which explains why they're so high. But these are actual numbers that were available during that game. And we've got all these Round Rock Express players. His batting average, Carlos, is .667. Jake is batting .600. So is Tyler. Thomas Tellis is batting .330, if you know anything about baseball. Kyle Blanks is .327, .325. So these are actually all really good batting averages. Above .300, you're doing pretty well. So are the probability of getting hits dependent or independent? Assuming we're not having to deal with any strategies of loading the bases, you would hope that your probability of getting a hit is not affected by the probability of the person in front of you getting a hit. So those should be independent. Now I'm going to start with the slightly harder example, and hopefully I won't lose you here. So we want to know, find the probability that Carlos gets a hit and Thomas does not. Well, Carlos getting a hit, his probability is .667, okay? And Thomas Tellis is over here at .33. But the thing is, I don't want Thomas to get the hit. I want him to not get a hit. So if I, right here, I'm going to do the complement, which is 1 minus .33. Let's see how well I can write with my mouse there. 3, there we go. This is why I mostly type it. All right, so that would be the probability of Carlos getting a hit and then Thomas not getting a hit. That little C right there means complement. So that C is the complement. If you probability of rain is 40%, the probability of its complement, not rain, would be 60%. Hopefully you're getting that gist. So this is the 1 minus .33 that I told you about, and there's a .667. Multiply them out, and you get an ugly decimal number. Hanser Alberto, let's see if I can do pointer options. In color, we'll do a different color. Hanser Alberto is up here. Where is he? Here he is, .302. And Kyle Blanks is .327. This time I just want them both to get a hit. So those are the probabilities I want. I'm going to multiply them together, and I get another decimal value. Okay, now let's take a look at an example where we roll a die twice. First of all, are the two rolls independent or dependent? They're independent because it's not like faces of a die disappear or you have fewer of them. So I'm just going to multiply the probability of getting a 5 first and then an even. There's only one 5 on the die, so that probability is 1/6. Probability of an even is 3 out of 6, or 1/2. So I multiply both of those and I get 1/12. What's the probability of rolling an even number and then a 5? Well, it's basically the same thing. It's just switching the two numbers and I get the same answer. Now here's a little twist. What is the probability of rolling an even and a 5 in any order? Well, that's the same as saying we can roll 5 and then an even, or an even and then a 5. With OR probabilities, let's say I had a lot of you made A's on the last test. Let's say 60% of you made an A and 20% of you made a B. What percent of my students made an A or a B? You will naturally say, oh, it's 20% plus 60%, it's 80%. And that's true for probability as well. There's no overlap there, so I can just say, 1/12 plus 1/12 is 2/12, also known as 1/6. So we're going to look at this OR rule again here because there's a little piece I need to show you on that. Notice I had said the word as long as they don't overlap. Oh, by the way, this symbol right here means OR. Okay. If I rearrange the rule here, I get the conditional probability rule, which is, this is an aside here. And I get probability of A given B is probability of B and A over probability of B. And in the next set of notes, we will be going over how to use this formula. All right, but save it. And that symbol right there means and. So let's go ahead and revisit the urn with the 4 marbles. We've got 2 red, 1 green, and 1 white. And we're drawing with replacement. So it's like the very first example we did. And there are all the sample space outcomes. I just went ahead and wrote them there instead of like trying to do the whole tree. So I want to determine the probability of getting a green marble on the first or second draw. I'll go ahead and highlight every one of these up here that have a green or a red marble. And there they are. And if I count them, 1, 2, 3, 4, 5, 6, 7. There's 7 outcomes out of 16. So the probability of rolling a green first on the first marble or the second is 7 out of 16. And that is the right answer. The sample space sometimes can be the easiest way to get the right answer quickly. Now, some of you like to do formulas and steps. You're like, well, let me go ahead and just add them. What's the probability of a green marble on the first draw? Well, that's 1 out of 4. And what's the probability of it on the second draw? It's 1 out of 2. 1 out of 4. When I add those, I get 1/2. But that's not the same thing as 7/16. And why is that? Well, we're double counting this one right here. And when you double count, that increases your answer. And if you just do a formula without thinking about it, you'll get the wrong answer. You'll be a little high. So we're actually going to adjust the OR probability formula. It's not just adding the probability A plus the probability of B. We need to subtract out anything that's double counted. So if I do it this way, probability of green on the first or green on the second is 1/4 plus 1/4 minus how many outcomes have it happening all at both of them at the same time? It's just the 1 out of 16. So 1/4 plus 1/4 is 1/2 or 8/16 minus 1/16 is 7/16. And let me go ahead and show you one more example to make you a little more comfortable with this rule. We're going to just roll a die. And what's the probability of getting a 5 or an even? Well, the formula is 5 or even. Probability of a 5 is 1 out of 6. Of an even is 3 out of 6. There's no overlap. I never get a 5 and an even at the same time on one roll. So it's just 4 out of 6 or 2/3. Now, what's the probability of rolling a 4 or an even? Well, probability of a 4 is 1 out of 6. Even is 3 out of 6. And how many are 4 and even at the same time? 1 outcome, which is a 1 out of 6. So we just get 3 out of 6 or 1/2. So that gives you a little better idea about how the OR probability works.